Shanawaz. In this lecture we will be doing the direct sum of subgroups of an abelian group. There are two ways to describe the direct sum of abelian groups, say S1, S2 through Sn. The easiest version is sometimes called their external direct sum, which we denote by S1 times S2 times through times Sn. Now this is a set whose elements are given by n tuples, i.e. the set contains elements of the form say little s1, little s2 through little sn. Now these little si's, they belong to these capital SIs. Now this is a set which contain n tuples. We claim that this set is a group with respect to the binary operation defined by, suppose we have two elements over here in this set, S1 cross S2 through Sn. Suppose we have two elements over there, say S1, S2 through Sn, and T1, T2 through Tn. Now we define their sum to be the component wise sum, that is first component is added with the first component over here is S1 plus T1, S2 plus T2 plus so on Sn plus Tn. Now we claim that this set over here, this is a group with respect to this binary operation. So one can easily prove the axioms of a group. For example, identity of this group is identity element of this group is the element 0 0 through 0 0. Now since each Si is an abelian group under addition, so they must contain the 0 element. So this definitely belongs to S1 cross S2 cross so on cross Sn. So this serves as an identity element, since S1 little s1 comma little s2 so on comma little Sn plus this 0 0 0, this is same as little s1 so on little Sn, and this is same as 0 so on 0 plus little s1 so on little Sn. Now this is true for all elements in S1 cross S2 cross so on Sn. So this is true for all S1 through Sn in S1 cross so on cross Sn. Now as far as the existence of inverses of elements in this group is concerned, we claim that if S1 through Sn belong to S1 cross so on cross Sn, then minus S1 through minus Sn is the inverse of S1 through Sn, since S1 through Sn plus minus S1 through minus Sn. This is the identity element 0 0 through 0, and this is same as negative S1 through negative Sn plus S1 through Sn. So this serves as an as the inverse of this element over here. Finally, for the associativity, let us consider S1. Now this is the element in our running group, T1 through Tn, and say P1 through Pn. They belong to S1 cross so on cross Sn. Now S1 through Sn plus T1 through Tn plus P1 through Pn. This is same as S1 plus T1 through Sn plus Tn plus P1 through Pn. This is same as S1 plus T1 plus P1. It is like this, plus so on plus Sn plus Tn plus Pn. Now these are the elements in these subgroups. Now these subgroups are abelian, so we can write this as S1 plus T1 plus P1 through Sn plus Tn plus Pn. So this is same as S1 through Sn plus T1 plus P1 through Tn plus Pn. This further equals to S1 through Sn plus T1 through Tn plus P1 through Pn. So this shows that this set is an abelian group with respect to this binary operation. There is now the other way to describe direct sum of these abelian groups, which is the most useful version, that is isomorphic to S1 cross S2 cross Sn. So that is called internal direct sum, i.e. if we have any group which is isomorphic to which is isomorphic to S1 cross so on cross Sn, then in that case G is said to be the internal direct sum of these subgroups. Now this is the external direct sum of these SIs. Now any group G which is isomorphic to this internal direct sum, then that group is called the external direct sum of these subgroups. So let us move to the definition. Let us consider a group G. Let G be an abelian group and S and T are at subgroups. With G equal to the sum S plus T. Now this S plus T, this is the set which contains elements of the form little s plus little t, where this little s is in this big S and this little t is in this big T. Now this set S plus T contains elements of this form. So here it is given that G is of the form S plus T, that is every element of G can be expressed as sum of an element in S and an element in T. So if G is such that G is equal to S plus T, where this S and T, their intersection is singleton 0, obviously if S and T are subgroups of G, they must contain the identity element of G. So 0 is here and 0 is here as well. Now if S and T are such that their intersection is only in the singleton such that their sum is whole G, then in that case G is called internal direct sum of S and T. Then G is called direct sum, then G is called internal direct sum of S and T, and is denoted by that is G is direct sum of S and T, i.e. G is S, and this notation over here, this is called O plus. This G is S O plus T. Now this O plus stands for the internal direct sum. This means G is S plus T and S intersection T is singleton. Now let us prove a proposition. Now before proving this proposition, let us do some preliminaries. So let us suppose G is a set which contains elements, say 1, 2, 3, 4, 5 and 6, and G prime, which is given to be equal to subset of G, it contains elements, say 1, 2 and 3. Now here G prime is subset of G. In this case we can always define an injective map from G prime to G. So we can define an injective map from G prime to G. This is our G prime, this is our G, where 1 goes to 1, 2 goes to 2, 3 goes to 3. Now this map is called the inclusion map. So if S is subset of T, we can define a map I which takes elements in S to T. Elements in T. Now note that if small s is in here, this s also sits in T. Now this inclusion map, this takes this s here to the already existing element in T. So this inclusion map is sometimes defined like this: curved hook arrow. So this means inclusion. Now let us do a proposition. Now this proposition the proposition states that the following are equivalent for an abelian group use acronym. The following are equivalent for an abelian group G and its subgroups S and T. It is given that let I from S to G and J from T to G be inclusions. So first condition is G is direct sum of S and T. Second is for each G in G there exists unique small s in S and small t in T such that this small g is little s plus little t. A third condition is there are homomorphisms P from G to S and Q from G to T such that P composed with I is identity map on S, comma, Q composite with J is identity map on T, P composite with J is 0 map, and Q composite with I is again 0 map, and finally I composite with P plus J composite with Q is identity map on G. So we have to prove these conditions are equivalent. First we'll prove first implies second. We'll assume that G is direct sum of S and T. Then we show that each element of G can be uniquely expressed as sum of an element of S and an element of T. So proof. First implies second. So we are going to consider that G is direct sum of S and T. Let G be the direct sum of S and T. Now if G is direct sum of S and T, this means G is S plus T and S intersection T is the singleton 0 by definition of the direct sum. Then G is S plus T and S intersection T is the singleton 0. Now this is definition because we write O plus for these two things. Now what we have to prove is that we have to prove each element of G can be uniquely expressed as an element of S and an element of T. Let G belongs to G. Now since G is in G, by this hypothesis over here we have G is equal to little s plus little t, where little s is in S and little t is in T. Now this follows from here. Now what we have to prove? We have to prove this representation is unique. Now let us suppose there is some other representation. Let G is called S prime plus T prime, where S prime is in S and T prime is in T. So comparing these two over here, we have S plus T, this is equal to S prime plus T prime, or S minus S prime is same as T prime minus T. Now S is in S, S prime is in S. Now S being a group, S minus S prime is in S, so this element is in S. This belongs to S. So this belongs to S. Similarly, T prime is in T, this little t is in T, so this element is in T. But these two elements are equal. This means this element is in S as well as in T. Similarly, this element is in S as well as in T, because these two elements are here and are equal to here. So this implies S minus S prime is in their intersection, because if something is in S as well as in T, then that something is in their intersection, and T minus T prime is in S intersection T. Now, by hypothesis, S intersection T is singleton. This further implies S minus S prime is 0 and T minus T prime is 0, or S is same as S prime and T is same as T prime. So this implies that second is valid. We have proved that each element of G can be uniquely expressed as a sum of an element in S and an element in T. Now, second implies third. Now, we'll assume that each element of G can be uniquely expressed as a sum of an element in S and an element in T, and we'll prove those equations are valid. Let G belongs to G, then G is equal to S plus T, where S is in S and T is in T are unique, because we are assuming second to be true. Note that the functions which are given, the functions P from G to S and Q from G to T are well defined. Because this follows from hypothesis, are well defined because of uniqueness hypothesis. Uniqueness hypothesis. Now see, if this uniqueness ceases to exist, then what will happen? These functions won't be well defined, because in that case G, if this expression is not unique here, then G will be equal to S plus T as well as S prime plus T prime, where S prime is not equal to S and T prime is not equal to T. In that case, P of G will be S as well as P of G will be S prime. Because this P, this is they are actually called the projections. Now given that S and S prime are not equal, this implies P of G is not equal to P of G, and which is absurd. So this makes sense only when this S and S prime are equal. Similarly, we can show that Q is well defined, which follows again by the uniqueness hypothesis. So these maps are well defined. It is given that these maps P and Q, they are homomorphisms. Now we have, now what we have to prove first, P composite with I, this is identity on S. Sorry, this is capital S here. See, this I is a map from, this is actually inclusion map. This is a map from S to G, and this G, this P is a map from G to S. So their composition, P composition I. First we are composing I. Now I is a map from S to G, and when we operate P is a map from G to S. So P composition I is a map from S to S. Now we have P composite with I is a map from S to S. Such that P of I, when we operate this map on some element of S, say little s, what will we get? Now this is P of I of S. Now S is subgroup of G, that means S is subset of G. So we have the inclusion map. This is I. Now if it is S here, this S is mapped to S because this S is already here. So this S is mapped to S, which is same as I of S. So this is P of I of S. Now this is same as P of I of S is same as S. So this is same as P of S plus 0. Now this is now P is projection of G onto S. So this is same as S. Now this P of I, this behaves as an identity map on S. Now what is ID on S? ID from S to S is a map which takes every element S and maps it to itself. That is ID on S. Now this is same as P of I from S to S, because what P of I does on S, it takes an element little s in S and maps it to little s. So this implies P of I is same as identity map on capital S. Similarly, we can prove that Q of G J, this is identity map on T. This follows on the similar lines. Now we have proved these two things over here. Now we have to prove these two conditions. Now I want you to make it clear that a projection, say G is, suppose, direct sum of S plus T, or let us suppose G is S cross T, i.e. G contains elements of the form S and T. Now projection of G onto S is nothing but it takes an element of G which is of the form S and T and maps this element on the first component S. Similarly, projection of G onto T, let us note that by Q. So this, it maps this element to the second component. Now this is what we call a projection. So now what we have to prove? We have to prove P of J. Now see, J is a map from T to G and P is a map from G to S. So P of J will be a map from T to S. We have P of J a map from T to S such that P of J, when we operate this map on some element of T, it becomes P of J of T. Now J of T is nothing but a projection, the same as P of inclusion. This is T. Now T is in T, so this is same as P of 0 plus T. Now P is projection of G onto S, so this P of 0 comma T, this maps this element on the first component, and the first component over here is 0. So P of J behaves as a 0 map. Similarly, Q of I behaves as a 0 map. Now finally we have to prove the last condition, that I of P, I of P plus J of Q behaves as an identity map on G. So I of P and J of Q. Now I of P is a map from G to S and I is a map from S to G. So I of P will be a map from G to G. Similarly, J of Q. Now Q is a map from G to T and J is a map from T to G. So J of Q will be a map from G to G. Now both I of P and J of Q, they are a map from, they are the maps from G to G. So their sum will again be a map from G to G. Finally, I of P plus J of Q, this is a map from G to G, such that, now let us see what will happen to an element G when we operate this map onto that element. now such that I of P plus J of Q of this little g, this will be I of P plus J of Q. Note that we can write this g as S plus T, where this S is in S and T is in T. So this is I of P of S plus T plus J of Q operated on S plus T. So this is same as I of P of S plus T plus J of Q of S plus T. Now this P is a projection of G onto S, so this will give, and this will give us the first component of this element here. So this is I of S plus J of Q is a projection of G onto T, so this is T. Now I and J are inclusions, so I of S will be S and J of T will be T. Now S plus T is again T, so sorry, G. So we operated this map on G and we get G. So this map behaves as an identity map on G. Finally, we have to prove third implies first. Third implies first. So we have to assume that these conditions are satisfied. We have to consider that these conditions are given, where P and Q are the projection maps which are indeed homomorphisms, and I and J are inclusion maps with these conditions, i.e. P of I and J of J are identity maps on S and T, P of J and Q of I are zero maps, and this map I of P plus J of Q is the identity map on G. So we have to assume these conditions, and we are going to prove that G is direct sum of S and T. So let's consider, let G belongs to G. Now it is given that I of P plus J of Q, this is identity map on G. This means that if I operate this map on this G, we get G, that is G is same as when I operate this map on G. This is same as I of P of G, J composed with Q of G. Now this is I of PG plus this is J of QG. Now this element over here, this belongs to image of I plus this belongs to the image of J. Now note that I is inclusion map from S to T, and J is inclusion map from, sorry, this is G, and J is inclusion map from G to T to G. So image of I will be S and image of G will be T. So this is belongs to, so this is same as S plus T. So this means this G belongs to S plus T. Or on the other hand, in other words, so note that S plus T is subset of G. Now what we have proved here, we have proved here G is subset of S plus T. We took an element G in G and we proved that that element also lies in this set. So that is G is S plus T. Now it remains to prove that S intersection T is singleton. Now to prove that, to prove this, let us consider an element. If G, suppose this G is in S. If G is in S, now this, if G is in S, that means this G is I of some small s. Note that we have I, a map from S to G. Now this G is in G. Now we are assuming that this G is in S as well. So if G is in S and every element S is mapped to some element in G, because S is subset of G, every element of S lies in G. So if we have small s over here, this is mapped to I of S, which is equal to S. So if G is in S, so this G will be equal to some element, say S, such that G is I of S. This implies Q of G will be equal to Q of, now this G being an element of S, it has an expression of the form I of S. So this is Q of I of S. Now it is given that Q of I is 0, so this is 0. Similarly, if this G is in T, then P of G is again 0. So we observe that if G is in S, then Q of G is 0. Similarly, if G is in T, then P of G is 0. Now if G is in the intersection S and T, note that we have to prove that this intersection is singleton. We have to prove it contains only 0. Now we are taking G in this set. Now what we have to prove? We have to prove G is 0. Now if G is in this intersection, then G is same as I of P plus J of Q G, because this map serves as an identity map on G. So this is same as I of PG plus J of QG. Now If G is in this intersection, then G is in S as well as G is in T. Now if G is in S, in that case Q of G is 0. So in that case this element is 0 over here. If G is in T, in that case P of G is 0. So this is 0. So this is same as I of 0 plus J of 0. I and J being the inclusion maps, this is 0. So we have proved their intersection is singleton. This implies that G is S plus T, where S intersection T is singleton. In other words, G is direct sum of S and T.